Tarun, I think you're on mute right now.
Thanks for that.
Yeah.
I'm so sorry for
Yeah.
that problem
No
that
issues.
happened.
Yeah.
So, good evening, everyone. Today we have with us Mr. Kaushal Bhavsar from Omdena, and he will be presenting his talk on the topic increasing solar energy adoption using machine learning. So, before he starts with it, a bit of introduction about him. So, Mr. Kaushal is a technical mentor and lead machine learning engineer in Omdena with over 2 years of experience in AI and geospatial analysis. He has worked with startups and NGOs across the globe like Need Energy to identify energy usage in Africa, Child Growth Monitor to use machine learning to detect children malnutrition in India, Stanford University to identify illegal land occupied in Kenya, and many more. He specializes in computer vision and deep learning, and his expertise is climate change and still impact. So I guess that introduction. So just a moment, I'll just add to the stream. The stage is all yours. Hey Kaushal, you are muted.
I think it's going to be the culture now. It's going to be muted right now. I'm so sorry for that. A little bit more about me is that I've been working in energy sector, specifically renewable energy, specializing in solar energy for quite a time right now. Um, I am working towards using machine learning or AI or computer vision so that I can make an impact on climate change. This is one of the project that I commenced on last year, October 2020, 2020, and this was specifically focused on how we can use machine learning to increase solar adoption throughout the country. This project was partnered with Solar AI and Engie Factory. This actually project spent out to be an 8 week of intensive project where we tried multiple machine learning models and came up with a fun solution. A little bit more about the details in further slides, but before that, thank you so much for joining. Um, so let me tell you about what the problem is, why we started this project, what was the goal of this project itself. So since this project was based on Singapore itself, because the company Solar AI is focused on Singapore for now, I'll be talking more about the market of Singapore and what is the culture there. But this is actually applicable to all around the world, sometimes higher, sometimes with lower intensity. But this is somewhat the similar situation around the world. So what happens is in solar industry, as in from an individual house owner's perspective, it's very hard for an individual to gather the information to install solar panels as of now, because then you have to calculate the solar potential of your rooftop, how much it will cost, whether or not you will get any investment back, or is it the climate or the sun around you, is it appropriate for solar or not. So these are the basic information an individual might or might not know. Second, the investment that an individual has to keep on, it's not consistent throughout the world, right? So it's going to change. If your house is bigger, it's going to be a bigger investment as a smaller and smaller investment. So an estimation of that solar installment is not actually widely known. Secondly, the information of the knowledge of what solar can bring to the environment as well as the world, and how everyone in the entire world is shifting towards, every government is actually shifting towards renewable energy. It's not known throughout the world. So these are the barriers from an individual individual house owner's perspective, but there's also some barriers from solar panel installers as well. So for from perspective of solar panel installers, it's very hard for them to go to individual houses and actually calculate the measurement of rooftops and give all the customers an estimate. So generally, a smaller project like an individual household is very expensive for them for solar panel installers, and the profit margin is very low. Most of the, as I have mentioned, that most of the sales, like 30 to 40% of the whole project cost, actually goes into sales itself. Um, so usually what happens is the solar panel installers focus on bigger perspective or bigger projects like industrial area or someone or some real estate owner who has more than like 10, 20 buildings around the country or around the city. So these are the area where solar panel installers focus on, and so there is a huge market gap in between. So what Solar AI came up with a problem statement is that we want to minimize that the market gap by providing enough information and knowledge to the customers or the individual house owners, as well as reducing the cost of sales of for the solar panel installers as well. So this way we can get solar to each and every household in the country for now and in the world in the future. So what we came across is a product. So this is the final product which I'm showing you right now. I'll come to the how we build it and for the slides. So this is what our final product looked like, where actually you enter an address and we actually calculate all the solar potential in your building through satellite images. Um, so this is how the final product looks like when you see that you can save on electricity bill, how much you can save, what is the installment cost, and how many years it will take you to get the return on investment. And after that, how much you can save, what will be the recommendation installation size and the carbon emission reduction that you do per year, as well as how many cars or trees you have planted. So this is kind of an incentive to an individual house owner, because generally when you look at people, they will actually see their profit before like trying to save the planet, which is actually okay, which is actually very common, which we have seen. So we came up with project objectives on what we wanted to do and how we wanted to pan out throughout 8 weeks of project that we have commenced. So to actually calculate the rooftop potential of the whole building, we first started to actually localize the building, which is the first point, detecting the building outlines. After detecting the building outlines, we tried to detect the type of the roof. So when you look at the roof, there are three types of different rooftops. One is which is flat, which is a most common one. Second one is tilted on one side, like there's a shed roof, that's called a shed roof. And the third one would be a rooftop which is tilted on two or more sides. So it will be kind of a tilted hip roof is what we call that. There is more kind of where we have swimming pools and a lot of stuff and so on top of rooftops, but that's considered to be an outlier. So these type of roofs make a huge impact on the solar potential of a roof of a building. So let's say if it's a flat roof, the amount of sunlight it's getting will be different from a rooftop which is tilted from one or both sides. So that's what we try to detect on the second point. The third point would be estimation of the direction of the slopes if surface is not flat, because let's say if you're living in Australia, a rooftop which is facing towards north will be a better option, or will have better solar potential other than a southern building. And similarly, if you're living in somewhere in Europe, a building facing towards south will have better solar potential or higher solar potential. So calculation of the direction was very important here as well. Other than that, we also try to classify roof material between metal, glass, and rooftop tiles. The reason why, because it's generally harder to put solar panels on certain materials. For example, like glass. So if you want to put a solar panel on glass, you have to create a platform first and then put a solar panel, which actually makes a huge impact on the final estimation of the solar installment. Um, in comparison to metal, if you look at the metal, it's actually generally easier to put solar panels on top of that. We also want to detect obstacles on the roof faces, because when you see, you cannot put solar panels on top of air vents or chimneys. So anything which we cannot put solar panel on is considered to be an obstacle by us. Obstacle detection was also very necessary. Lastly, after calculating all those features, we create a final data set where we have free surface area available per building, per rooftop. And this is where we put that calculated area into a formula. In that formula, we also include the material and the tilt of the roof, or the flatness of the roof as well, to actually calculate the final rooftop estimation per building per rooftop. Sorry. So this is how we started. We actually gathered, we 52 collaborators from 21 different countries gathered towards one cause. We were people from Bangladesh, Brazil, Canada, Spain, Switzerland, Taiwan, and various more. We formed ourselves into self-organizing team according to our skill sets, and this was generally Omdana projects goes on for 8 weeks. So we commenced for an 8-week project for this particular course. And we, as a final output, as I shown you before, that we actually managed to deliver an output with rooftop features and fulfilling solar AI's requirement. This is how the pipeline looks like. So we started with satellite images. Solar AI gave us a satellite image of Singapore Island, and we actually used that satellite image to do some pre-processing. After that, we annotated. Um, as mentioned, we localized each and every rooftop and calculated its type, where it's called rooftop detection. Then we moved on to obstacle, material, and rooftop orientation detection, and then the final. So starting with pre-processing. So when you see satellite images, it's actually very huge. It's an image which is in gigabytes actually. So it's very hard to manage a huge satellite image. So what we try to do first is to actually make different tiles out of it. We don't call them images, we call them tiles, because it's not just an image. It has a lot of information available, like for example, coordinate reference system, the coordinates, the actual coordinates itself, the transfer information, and lots more. So we actually created multiple tiles out of single huge satellite image, and we did not just take out slices of tiles, because we don't want any building to get cut off in between. So we had actually used a sliding window approach, where we slided window with a little bit of offset, so that we don't miss out on anything. Doing this, we actually created a data set of 2000 plus tiles, and each and every tile would have more than around 400 or 500 buildings. So you can see that we had like millions of rooftops available with us. So generally, when you talk about machine learning, the very first thing what you want to do is to actually tell the machine what we are looking for, what we are actually set out to detect. So what we did was first to actually annotate each and every building or each and every rooftop, so that we can feed that initial data set into the machine learning models. So we did not just mark the rooftops as polygon, but we also marked each and every faces of rooftop as one single batch, and one single batch would contain all the all the all the roof mask, or all the polygon itself. We used QGIS, which is actually a tool which helps us with raster or vector data set. When we talk about a satellite image, it's a raster data, and QGIS helps us to use multiple features inside it to actually manipulate the raster data. So QGIS was our choice of the tool that we used to annotate, first of all. Secondly, we also used an OpenStreetMap. Those of you who don't know, OpenStreetMap is the open source map information available. So whatever you see on Google Maps, it's kind of similar to that, but it's actually open source and free to use. and people across the world have been contributing to it so that we can improve the map information. So we also use those information, OpenStreetMap information, to our advantage. I'll tell you how OpenStreetMap helped us in the further slides, but this is what the initial annotation looked like. So after annotation, we actually to do the annotation, we actually curated detailed guidelines for the annotators. We had like 20, 30 annotators working day and night to actually annotate all the buildings. We actually annotated hundreds of satellite images in batches, and we were able to actually annotate 700 images in 3 different batches. And this is what you can see below what how the masks looks like. It's pretty complicated, so we actually have to draw single mask across all the rooftops. And as I've told you, every single tile will contain actually 400 images, so it's actually a TTSL and long process. So this is where we spiced up things. This is what the sweet part of machine learning is. Generally, when you talk about a machine learning project, 80% or I would say 85% of the time would go into actually cleaning the data, gathering the data, and creating an ETL for the data. This is where we started working with how we are going to localize the building. So we use different convolutional networks like Mask-RCN, Detectron2, or ULAT. We try to not only localize the building, but also try to do an instance segmentation where we would classify between 3 different instances, which is flat, hip, or a shed roof. As I mentioned before, hip is tilted on both sides and shed is tilted on just one side. So we also try to calculate those, and as you can see that it gave us pretty good result. You can see the polygons on top of each and every building, as well as the labels across it. The numbers that you see around the labels is actually the confidence score. So whenever you try to do a machine learning model, it gives out, if you program it that way, it gives out you a confidence score, how much confident it is about the label that it has output. So as you can see that we even reached the confidence score of 1, which is pretty good, ranging from like 60 to 1. So it's a good score that considering the machine learning models. So after that, we moved on to obstacle detection as well. It's pretty important to actually calculate the obstacle detection because generally rooftops have a lot of obstacles inside them, and it plays a major role in solar panel installer. It plays actually very vital information to solar panel installers. So if you look at the buildings from a satellite point of view, the buildings are very small, and the obstacles are actually not quite visible to us, or annotating is like actually very hard. So imagine annotating each and every single rooftop, as well as annotating the obstacles on it, and you have 400 buildings per image, and then you have like 2,000 or 3,000 plus images, which is actually not feasible for an 8-week project. So we did not go and annotate obstacles at all. Instead, we moved on to an unsupervised machine learning algorithm where we actually use edge detection as well as color clustering method. So on the left, you can see the edge detection algorithm that we used, where we were able to actually define the obstacles. On the right, you can see that we have segmented all the pixel intensities on basis of their bins, or basically divided them into groups. So the darker groups that you can see here on the right image are the ones that are considered to be an obstacle, and the other ones are actually bad. So the obstacles that you see, we can take out the number of pixels that it covered or the area that it covered, and it gives us the final obstacle. We did not need to classify the obstacles because we don't need what are the obstacles on top of the buildings. We just need how much area does an obstacle covers. So the clustering method works wonders for us. After that, we moved on to the roof material information, because again, as I mentioned, this also plays an important role in the final calculation of solar potential. We use multiple neural networks. We train multiple VGG networks as well, and finally came up with a model that gave us greater than 80% of accuracy, which is actually pretty good, considering that we only had like 900 data points with us. Again, annotating material was also not an easy task for us, since given like the constraint of the time. We used OpenStreetMap, and actually OpenStreetMap for Singapore had 900 different data points inside them, which we could use for material training. We used those, and we trained another neural network model to finally come up with a solution. Things to note about this is that we can actually go and annotate, we can actually go and detect multiple materials across one single rooftop itself, because half of the rooftop would be roof type and half of the rooftop would be metal. But for this particular model, we ignored those. We actually tried to calculate all the materials that are available on the rooftop. For now, we actually focused on only 6, which is tiles, concrete, metal, glass, Ethernet, and grass. Generally, you can see that metal and tiles are most common ones. So there were some class imbalances between them. To actually manage those, if you are actually familiar with neural networks, we provided some class weights to them. So in putting it in layman's term, we told the machine on how important a single label is, or how important a material is. So the higher the example cases or higher the training labels we have for a particular class, we told the machine that we do have a high number of this class and low number of that class. So you might actually be biased on the high number of labels that we have. So we provided some class weights to actually balance those. A lower class weight to the high number of labels and higher class weight to less number of labels. That's how we managed the data itself. Again, as I mentioned before, most of the machine learning part is actually managing and trying to create a model out of what we have, trying to actually create a model for the data itself. So actually the data manipulation or the data wrangling or the data working is actually the major part of the machine learning process side. The last thing that we wanted to try out was orientation of the slope. As I mentioned before, orientation was important because the position of the sun in respect to the rooftop plays a major role in how much solar potential does a particular rooftop have. Again, annotating each and every phase and each and every slope of rooftop was not feasible for us. We already took a lot of time to annotate the roof polygons itself, so it was not actually feasible for us to do that. So generally, when you look at a problem statement which mentions that you need to solve X using machine learning, generally you think of solving all the problems inside it using machine learning or neural networks or deep learning or such algorithms. But generally, when you but simpler problems require simple solutions, and that's what we've gone here. Instead of moving to machine learning models where we required a lot of data, we actually used polygon estimation, pixel calculation, and mathematical approach to detect the edges of the rooftop as well as calculate the orientation. So what we tried to do was calculate the difference between the foreground and the background, and we calculated the rooftop, the edges of the rooftop. We calculated the prominent edge and tried to take out the points outside the prominent, connecting to the prominent edge. That's how we got a very complex roof polygon. After that, we used some simplification and polygon estimation techniques so that we could get a proper straight edge of the rooftop itself. Doing so, we did not require any data because it was purely mathematical. And this is where machine learning models fails, when you don't have a lot of data available with you, especially deep learning models where you don't have any data. We use some approximation and optimization technique, and we actually created our own algorithm to tackle the phase segmentation as well as orientation detection within that. So on the image on the right, you can see the orientation would be 140 degree northwest. This is calculated by taking the edge and the angle between the horizontal axis. We calculated the position of each and every edge with respect to the other edges as well. So as you can see that the red edge is actually have an same angle as the yellow edge, which is on south and the north. But since these two do not have the same angle or the same orientation, we had to calculate different angles for them. And the way we did it was that we said that, okay, we actually calculated the respective position, that the red edge is actually north of the yellow edge. So that yellow edge would have to have angle was facing south, and red edge would have an angle facing north. So we calculate an acute and obtuse angle from both the sides of the straight line, and that's how we came up with the final solution. After that, the final step would be to actually take all those things out and consider that and put them into a final pipeline, where we put in a satellite image and as well as an address or coordinate. Then we calculate all the first the rooftop type, it's the polygon, the obstacle material, and then we emit out either a data or we display that over the internet or over the web browser. So this is how we look like. This is an actual image of where we started, and we sat and planned out on a sprint. We spent like 8 hours, 9 hours continuously on single sprints over Discord. And we set up multiple meetings across the week. For estimation, for in one single week, we had like 12, 13 meetings, which is a lot for a project we are doing after our day job or after our colleges. So a lot of hard work has been gone to this one. Finally, the project objective that we came across was that we put a satellite image as an input, and we had a very hard-working team. And we also had an Omdena's collaborative approach, where there is no one guiding you, or there is no manager. We actually group ourselves individually or with our teams into different subtasks, and then we move on and try to solve those subtasks, and then we create the final product. As a final deliverable, we actually created an automated end-to-end working pipeline, which takes in satellite image and emits out a data set containing all the features of the rooftop. So yeah, this was the step moving towards increasing affordable and clean and carbon neutral energy. Yeah, that's about it. Thank you.
Sorry again, my mic was muted again.
Yeah, no issues.
So that was a great presentation. So would you like to take in questions now? We have 2 questions.
Yeah, I would love to have one.
Okay, so one of the question is, there could be some building surrounded by a longer one, shading some or entire part of the roof, in brackets, blocking the sun rays. How would you identify that?
Okay, so when you consider a satellite image, it does not just only have a red, blue, and green channel. It also have some different channels as well. For example, an infrared channel. And if you talk about an infrared channel, it does not get affected by shadows. It actually gives you a proper information around it. When you feed in those infrared channels into a convolutional neural network, it gives you pretty accurate masks around the buildings itself. Also, yes, we do have some buildings that were shaded by not only big buildings, but also trees, that you have a big bushy forest around a single building. So the forest actually covers the building itself. So these are some of the outlier cases. As mentioned, like machine learning models are not 100% accurate. There are some anomalies, but these can be these examples can be taken into account by training more examples or either doing some pre-processing. So what we did to actually include those buildings was, first of all, increase more example having shadowed buildings. Since we had like millions of rooftop, we could not annotate all the millions of rooftop. We actually focused on annotating buildings with and without shadows as well. So that's why we also considered the shadowed buildings for rooftop polygon extraction as well. Yeah.
Another question, which is a bit more on the technical side. Can we consider polygon estimation as a classification algorithm?
Well, not. You cannot actually consider that as a classification algorithm. Um, the reason being that in a classification algorithm, you try to differentiate between different objects. So, for example, if you have a data set of cats and dogs, um, then you would need a classification algorithm to actually differentiate between if there is a cat or a dog in the image. But let's say you have a data set of pens, and what you want to do is basically try to localize pens inside a building. Or a very common example is where is Wadu, right? Wadu, where you have to actually figure out where that cartoon character is in a bunch of different characters in the image. So you don't actually need to classify all the different objects. You just need to find that one single object, right? So when you try to detect the edges of a building, I don't care if the building if the edge is north, south, east, or west. When I want to detect it first, but when I detect it, then I can calculate the respective position, and then I can calculate the north, south, east. So that's not actually a classification algorithm.
Okay, I guess we are done for the day. So
Okay, that's awesome.
thank you
Okay.
again. Thank you again, Kaushal, for coming in, and it was great to have you today. I have learned a lot today, so thank you so much.
Yeah, thanks. Thank you all for joining, everyone who has joined in. And that was some great questions. Even if you have more questions, I would be happy to you if you can mail it to me. I'll be happy to answer those over. And thank you so much, Tarun, for having me as a guest.
Thank you so much.